3, predicting the mass of a black hole using GlowScript. The principles behind this lab are Newton's second law and the momentum principle. The momentum principle states that the net force is equal to the rate of change of momentum, dp dt, where momentum is mass times velocity. dp dt is comprised of parallel and perpendicular components, where dp dt parallel is the final momentum minus the initial momentum over the change in time, delta t. This establishes whether the object is speeding up or slowing down. And dp dt perpendicular is equal to the mass times velocity squared over r, where r is the radius of the kissing circle. And this establishes whether the object is curving in motion and or changing directions. In this lab, these principles will be used to calculate the mass of a black hole, which will be the only force acting upon a star as it orbits in space. Initial values given to me for this lab were delta t is 1 Earth day, or 86,400 seconds. The mass of the star is 2.0 e 30 kilograms, and t equals 0 because we are starting at 0 seconds. The only force acting upon the star as it moves through space is the gravitational energy or force of the black hole with unknown mass. So I plugged all of these equations into GlowScript, and this is the code that I came up with. I derived all these from the momentum principle and in second law, where I found the initial velocity, the final velocity, initial momentum, final momentum, change in velocity, change in momentum, dp dt, net force equals dp dt via the momentum principle, and all of the other corresponding things that I would need to use to find the mass of the black hole. And then this is the second part of my code. This is not as important as the first one, but here I've established R, which is the magnitude of the change in position, and it's defined as magnitude of star's position as the star is compared to the origin, and the origin is the position of the black hole here. And then the mass of the black hole is calculated using net force times R squared over G times the mass of the star. And so when you run the GlowScript code, you get this orbiting star around a black hole. The star is the yellow dot, the black hole is the black dot. And given the results of the code displayed to the left, one can observe the mass of the black hole is 1.223 times 10 to the 34th kilograms. The code has also established that the net force is 1.497 times 10 to the 28 newtons. Parallel component of the net force is 1.497 times 10 to the 28 newtons, and the perpendicular component of the net force is 8.256 times 10 to the 28 newtons. Follow-up question is, if you knew the mass of the black hole and the mass of the star, how would you calculate on paper the net force on the star by the black hole? Doing this analytically, we have established the mass of the black hole from the code previously, the mass of the star, the initial velocity and the final velocity, and the net force is the net force parallel plus the net force perpendicular, and we have established those equations early on in the lab. Therefore, I would calculate the net Fnet and parallel and Fnet perpendicular separately using the formulas described earlier in the lab, which would then give me the values described in the last slide seen here, 1.497 times 10 to the 28 newtons and 8.256 times 10 to the 28 newtons. And then I'd add those together, and I would get the net force. Another way to do this is to calculate net force using the gravitational force and potential energy of the black hole in the star. However, we would focus on the first method in this lab. And so the parallel versus perpendicular components discuss how the net force and its parallel perpendicular components are different from the rate of change of momentum in its parallel and perpendicular components. Numerically, they are the same via the momentum principle, where Fnet equals dp over dt. Therefore, Fnet parallel equals dp dt parallel, and Fnet perpendicular equals dp dt perpendicular. This means that the parallel and perpendicular components are the same as their respective dp dt parallel and perpendicular counterparts. The rate of change of momentum versus net force. Think about what the rate of change of momentum means and what net force means. Are these different mathematically? And are these both things you can observe directly, or is one derived from the other? Mathematically, the net force is the sum of all forces acting on a system, while the rate of change of momentum is measured by analyzing the motion of a system. Therefore, these are very different mathematical processes. However, one can say that the rate of change of momentum is derived from the net force, as the net force causes a change in motion and therefore determines dp over dt when it is not equal to 0, which is seen in this lab. Both the net force and dp dt have perpendicular and parallel components and are numerically, but not mathematically, equivalent via the momentum principle. And then predicting the mass of a different black hole given the same conditions. No, it is not possible to find the mass of black hole 2 that is different from the mass of black hole 1. This is because I have calculated the mass of black hole 1 through the position data points of the star given to me and its corresponding velocity. If black hole 2 has a different mass from black hole 1, the velocity and position data points of the star should be completely different due to the momentum principle and Newton's second law. But however, in this example as described, you cannot, we would be trying to calculate a different mass based on the same data points, and that's just not possible here. Thank you.